Welcome back to the AGU Inspire stage. Please welcome your moderator, Michael Wimberly.
Whoa. Thanks a lot. I'd like to thank everyone for coming, making the effort to get back from lunch for this session. This is something that I'm really excited about, and I'm excited that we have assembled this great panel to contribute to our Science Nexus Day. I'm not going to give a long talk because I want to get to our speakers who are really going to have the interesting things to say here. But to start out, I really just want to make the point that when we're working at the Science Nexus, when we're trying to do transdisciplinary work, what it really comes down to is that our common currency, our common denominator is the data that we work with and that we base our science on and that we hopefully ultimately can use to make better decisions. But that is also one of the great scientific challenges that we deal with at the Science Nexus, figuring out how to access, harmonize, and analyze the ever-growing wealth of data that's out there across a variety of disciplines. And to address this important topic, we're really fortunate to have 4 speakers today who come from a diverse set of disciplines and have a number of really interesting talks to present to us. And so to start us out, I would like to introduce John Balbus. He's the Senior Advisor for Public Health at the National Institute for Environmental Health Sciences. He also serves as the Health and Human Services Principal for the U.S. Global Change Research Program. John?
Thank you. Thanks very much, Michael. Good afternoon, everybody. Hello. I'm going to add to Michael's welcome to you after your 7-minute lunch. I hope there's no indigestion out there. I'm going to start us off by talking a little bit about the types of Earth observation data that get applied for public health, some of those applications, and then I'm going to introduce the concept of precision public health as one frame to think about that kind of activity. Now, we are from diverse backgrounds. I'm a medical doctor, and so as a medical doctor, I was trained initially to synthesize diverse kinds of information, qualitative, quantitative, in order to make diagnoses and to be able to help my patients. And now in my role as a person at the Environmental Health Sciences wing of the NIH and with the Global Change Research Program, I'm working to incorporate lots of different kinds of environmental data, health data, in order to serve societal needs to help health. So I'm going to do this through the eyes and the lens of another doctor, a guy named John Snow, who some of you may know John Snow's story. If we could start the video, please. And to take us through the eyes of John Snow, I'm going to take us on a trip back through time and space to London, and the year will be 1854. Now, this is not London in 1854. Google Earth is pretty magical, but it could not actually get an image from space of London in 1854. But I'm going to take us to a particular street corner where a particular water pump was located. And at that time, this neighborhood probably looked a little bit more like this. This is, for those of you familiar with the story, the Great London Cholera Epidemic. There had been successive epidemics of cholera that had ravaged the cities of the Western world on a decadal basis for about 70, 80 years. Of course, it had been a bigger problem in places like India for many years before that. But the living conditions had made this a major problem. And the prevailing theory at the time was that people got cholera by breathing bad air. It was called the miasma theory. And if it really smelled bad, people thought that gave you cholera. John Snow had a different idea. He just came up with the idea from his observations that it probably had something to do with the water, but he needed to prove it. And in order to prove it, he provides us with really the first example of spatial analysis for epidemiology, for the study of human diseases. What he did was go door to door, and he mapped the actual cholera cases and showed where they lived. And he collected different kinds of data. He collected the deaths, He collected what people's water source was, and he collected whether or not they perceived impurities of the water. So some quantitative, some qualitative information. And he made a map that looked like this. This is pretty good. You know, he did it with a pen and paper. He didn't do it with ArcGIS. And he was able to look at this and see very visually that if you stacked up the deaths, they stacked up right around this Broad Street pump. And he noted a couple of anomalies, like there were very few deaths in the brewery. None of the workers in the brewery died of cholera, but it turned out none of them drank water. They are on their lunch break. You know, they were actually, John Snow's the originator of epidemiology, and the brewery workers were the originator of the American Geophysical Union exhibition hall refreshment practice, and they just drank beer all day. So here are some of the lessons from John Snow's map. It really helps to be able to visualize things, especially if you're trying to convince people, but also if you're trying to figure things out. And he was able to integrate these different kinds of data, you know, onto the map, the residents and the water source. But very importantly, he didn't do it from space, of course, right? He did it by walking around and putting holes in his shoes. You know, we in the field call it shoe leather epidemiology. Others call it ground truthing. So 150 years later, what are we doing in this field to try to do the same thing, to understand the environmental causes of human diseases? And this is just a list of a lot of different kinds of data that are now being applied. And I think in our talks we'll hear some of these examples. There's a lot of work going on now to really locate people in space very precisely, especially in low and middle income countries where census and mapping may not be quite as accurate as it is in other places. There's a whole range of biological and physical exposures that can be obtained from remote sensing, whether that's looking at air pollution, whether that's looking at surface temperature or sea surface temperature, whether that's visualizing flooding, whether that's measuring the reflectance of soil and trying to understand soil moisture or land cover. There's a lot of chemical exposures that are really important to infer from space. Some of that could be visualizing point sources, like mines that have lead tailings where people get exposed, or we're using this a lot now for air pollution. So many, many different kinds of data are now being applied for all different kinds of diseases, and this is really starting to be applied to addressing some of the major public health problems, whether it's pandemic diseases, whether it's emerging infectious diseases like dengue and chikungunya and Zika, whether it's even chronic diseases, like the increasing death toll from cardiovascular disease and respiratory disease associated with air pollution, which, as all of you I'm sure know, kills more people than the major diseases, tuberculosis, HIV and malaria, all combined. So I'm just going to walk you through a couple of examples where we're working on this. This is a paper that just came out recently, and it's about trying to improve a very important project in public health. It's called the Global Burden of Disease. It's produced by the Institute for Health Metrics and Evaluation at the University of Washington, and it has become one of the definitive sources of where people are, or in a very explicit spatial way, in every country of the world, what are people dying from, and what are the risk factors that they're exposed to that are contributing to those deaths. There are some environmental factors in it. It looks at air pollution, and especially particulate matter. It looks at lead exposure. It looks at radon and some occupational exposures. But for those of us in the environmental health field, where we're looking at all different kinds of exposures, from pesticides to mercury, arsenic, other heavy metals, to all the new classes of endocrine disrupting chemicals that we're seeing more and more problems with, the perfluorinated chemicals, it's missing a lot. And so there are a lot of us in the field who are trying to figure out how can we expand that. And one of the critical questions is, this is global. We know that people are exposed all over the world, but we really have a hard time figuring out what their exposure is so that we can quantify it and model the disease. So I'm just going to take you through a little bit about, first of all, the global burden of disease. For those of you not familiar with it, it is a really cool visualization of health around the world. This is just one screenshot that I took from their Global Burden of Disease Compare, GBD Compare. And it's just showing the cumulated disability associated with environmental exposures around the world. And you can see that sub-Saharan Africa, Southern Asia are the places that light up the most with that. And the Global Burden of Disease Project, which is a $240 million, very big project funded by primarily by the Gates Foundation, has decided that actually to intervene in public health, you have to get beyond the country level. You can't just look at a country and figure out where the problems are and where do you intervene. You have to get spatially much more explicit. And so they're trying to figure out ways to do this in every country of the world, to go down to the subnational level, to the state level. So I'm just showing here one example. They're piloting this. One example where they're looking at the state level in sub-Saharan Africa and mapping the malaria prevalence. And it's because not every state is the same. You can't take the average across all of the states in Nigeria, for example, and come up with a targeted approach. So this is what we're calling precision public health, and I take us back. This is a cartoon image of Jon Snow using his brawn and snapping the handle of the Broad Street pump in a very dramatic fashion. I think actually he stood back and had some other people take the handle off with a wrench, but this was precision public health, right? He decided where the problem was. He used his tools, he used his data integration to say, the problem is here, we're going to do something about it here and now. So the definition of that I'm going to throw out for precision public health is the right intervention at the right place at the right time. And for those of you familiar with public health, you know that's really hard to do. Our data sources aren't good, especially on the health side. We often find out about epidemics when they're raging, and by the time we can mobilize the intervention, they're ending. And you know, it looks like we did something, but it's too late often. The epidemic has already run its course. So the idea of precision public health, the right intervention at the right place at the right time, which is before people are dying of cholera in the streets. And so this is another slide. I'm sorry, it's a little hard to see. All you can see there are a lot of lines and a lot of fuzz for many of you, and that's enough to know. This is also from the Global Burden of Disease, and this is trying to map the under 5 childhood mortality rate at a subnational level in all the countries of the world. Okay, so that's why there's so many points on the x-axis. That's all the countries in the world with those 3-letter acronyms. And the point that you see there is very, very widespread variation within country in under 5 childhood mortality. And again, trying to get to the right place, trying to have your interventions be in the right place, and then the question is, how do you get it at the right time as well? So I'm just going, for those of you interested in this term precision public health, there are different schools of thought right now in our modern technological world. There is one school of thought that says, well, precision public health is understanding the genetics of everybody in a really precise way and where they are. And then you figure out, okay, well, most people have this gene, that, therefore we can use this vaccine or this set of drugs. So it's a very genomics-based idea that really correlates with the idea of precision medicine that the NIH is doing. The other is a much more AGU-friendly definition of precision public health, which is trying to integrate multiple kinds of data to get to the right place at the right time, basically. So these are some of the ideas that have come from this pollution health initiative that I started with, that article, that we need to expand exposure data sets, that we need to improve our source apportionment, and that gets done with multiple sources of data, imagery about point sources and what those point sources are, to publish more exposure data sets, to get them out into the published peer-reviewed literature, which is how the Global Burden of Disease team pulls them into their project to get more precise, and then also to build the epidemiologic evidence for new risk factors, which requires new ways of finding the exposures for things that we don't know how to do exposure assessment for as well at this time. I'm just going to tell you very quickly about initiatives that are going on within the global group on Earth observations. We now have, we have had for a number of years, led by John Haynes of NOAA and Julie Turton John Haynes of NASA, Julie Turton of NOAA, an initiative on public health within the group on Earth observations, and we just were elevated from a community of practice, which was cool, up to an initiative. This is the mission of our initiative, to foster the development of integrated information systems, and I'll put to you that integrated information systems are a key process step on the way to precision public health. And these are the work groups that we have, just to see it's very disparate kinds of things: heat health, air quality, vector-borne diseases, other waterborne infectious diseases like cholera, food security, and then healthcare infrastructure resilience. And I'm going to talk very quickly about this project that we're doing just as an example of how you can integrate many different types of data in order to serve public health purposes. And this is a project that is trying to combine a very detailed analysis of high-resolution imagery to geolocate healthcare facilities and be able to say something about their immediate surroundings, to assess whether they are in danger from landslides, from forest fires, what is in their proximity, are they in flood zones, and then to be able to also look at transportation routes, communication infrastructure, other forms of infrastructure, and assess its vulnerability in case of an extreme weather event, earthquake, etc. In closing, I'm just going to talk a little bit about my institute, the National Institute of Environmental Health Sciences. We are actually the public health wing, if you will, of the National Institutes of Health. So when I talk about precision public health, that's something that is of keen interest to this institute, where most of the institutes are a little bit more into the precision medicine side of things. We like that too, of course, but we're thinking about the geospatial and the environmental factors that are responsible for ill health. You can see this is the core strategic plan diagram, where we're working on advancing the science, promoting that translation, and also playing a leadership role in stewardship and support. And these are some of the ideas that are highlighted in our plan, including the idea of the exposome, which is integrating all of the different kinds of exposures we face: psychosocial stressors, chemical exposures, air pollution, etc. And you can read the other slides there as I'm running out of time. But we're also very interested in knowledge management, data management, and the use of very large data sources, such as remotely sensed data. I'm going to close with a discussion of some of the challenges to be overcome. I think I've highlighted some of the opportunities. Anytime that we're working with public health, we have a problem with data gaps. Many of those data gaps come from the health side. It's very hard to collect health data. It's extremely hard to collect health data in real time, and even harder to make it geospatial. There are a lot of privacy issues around the world. There's also in many countries an issue of political corruption, where census data and other kinds of data are deliberately biased in order to get to change resource allocation. There's problems of mismatch of temporal and spatial scales, where the health data lag real time, or it's very hard to get the gridding of the data at the same level. Many places we're still learning how to work with these disparate data sets, how to do the kind of geospatial integration, how to be able to manage them. And from the Rockefeller, just a lot of problems with privacy protections in a lot of places, which either inhibit the release of the data or make it hard to, or cause harm to people from the use of it. So with that, I'm going to close and just leave you again with this video of 2017 and the various forms of health-harming exposures. You see here on the bottom right, the Saharan dust, which has been associated with diseases in the Caribbean, also in the Mediterranean. You can see up in the top left the wildfires causing huge plumes of smoke, exposing people all around the world. And then you'll see some hurricanes forming. So this is a great example of both visualization to make it clear how the environment affects our health, as well as the ways to combine many different kinds of data for effective visualization. So thank you very much.
Thank you, John. That was a wonderful talk. Let me just say that our plan is to hold questions until all the presenters have talked. And at that point, we will have plenty of time for questions and also for some discussion amongst our panel. Now I would like to introduce Olga Wilhelmi. She's a research scientist and head of the GIS program at the National Center for Atmospheric Research. Olga?
All right, thank you so much for organizing this panel and for inviting me. I'm really glad to be here. So this is a Nexus interdisciplinary panel, and since I'm a geographer, I might be a little bit biased, but I feel like fundamentally geography is the foundation for interdisciplinary or transdisciplinary research. If we focus on a place or a space, it helps us to bring different concepts, different ideas, different data to the same synthesizing medium and answer a lot of different questions and resolve different problems that we have with diverse data. So today I will be talking about some of the work that we're doing at the NCAR with our collaborators on different aspects related to interdisciplinary research, and in particular on work that we do on better understanding and reducing societal risk to extreme weather events, climate change, and other environmental stressors. So our program focuses on interdisciplinary science, spatial data, interoperability, and knowledge sharing with GIS. And as I mentioned, we do diverse research that helps us to address some of those big problems. We also develop tools and applications that helps to increase usability of weather and climate models, particularly for the GIS community, and also to build capacity at the science and society interface. So we know very well that we live in a world that's changing very rapidly. By 2050, it is projected that the world population will reach over 9 billion people. And there is a lot of different, very pressing societal issues that we face right now. Those include growing population, aging population, rapid urbanization, different issues related to security, water, food, energy security, public health, as we just heard before, and also weather extremes and how all of those different phenomena affect our society. So when we think about all those different risks, how do we understand and reduce the risks? We need to put them together in interdisciplinary conceptual framing. So we can look at this intersection between weather and society in the context of changing climate, in the context of changing population, and also look at how different adaptation strategies and impacts of extremes on society, how they further may affect vulnerability of the population. And by vulnerability, we typically look at exposure, sensitivity, adaptive capacity. Some of this phenomena we know better, some we know less about. For example, there have been many years spent to better characterize and quantify exposure of different environmental stressors on population. We know a little bit more about sensitivity of population and infrastructures. We're dealing with some of those extremes. But we still know very little about adaptive and coping capacity, and that's where some of the social and behavioral science becomes really important, and integrating different data from all the different disciplines help us to understand the system and also reduce the future outcomes. So I'm just going to give a couple of examples from our work, those related to storm surge and coastal flooding and urban extreme heat. So we'll start with storm surge. So as you know, many people in the US and all over the world who live near the coasts are experience threat from coastal flooding, especially during hurricanes. And many people not aware that storm surge accounts for nearly 50% of hurricane-related human mortality. Hurricanes are getting better predictions, so we're seeing a lot of improvement in predicting hurricane tracks, as we've seen more recently. But despite those advancements, storm surge is really very difficult to predict. A lot depends on the storm size, on the storm characteristics, and also the characteristics of the coastal environment. Again, this is where integration of data becomes really important. There is a lot of uncertainty about this prediction, so we also need to figure out how do we help local population, coastal population better understand their risks. We can map tracks, we can map sensitive areas that we think may be experiencing storm surge. But how to put this information in a form that population can understand, that still remains a bit of a challenge. And so here in this example, we're bridging different disciplines, we integrating storm surge models, storm surge forecast with the features of local environment, topography, vegetation, buildings, roads, all the local infrastructure, to demonstrate how the water may be flowing inland. And at the same time, we're advancing some of the geospatial technologies by demonstrating the space and time dimensions and hopefully illustrating how the water not only may be affecting beachfront property, but may be coming from through river systems, through some of the complex hydrology of the coastal environment, and how quickly the water may reach very unsafe levels. So educating the public and communicating risk requires this very interdisciplinary approach in the use of technologies. We're also working with local communities. Again, that's where integration with social science research is extremely important, because not only we learn about some of the local vulnerabilities that we may not know from just looking at census data, but we also can test some of the approaches that we're developing and make sure that the maps, visualizations that we're putting out are easily understood, they're effective in risk understanding, in risk perception, and can help people make decisions. And we're also experimenting and looking, exploring sense of place. So we want to make sure that the information we provide is relevant and meaningful and can help people make better decisions. Now switching to extreme heat. So cities in particular are experiencing a lot of extreme heat waves. Our climate is warming. Our cities are warming at a faster rate, so some of the surrounding areas, and heat is a serious public health concern. So to provide information again to the public, so data access is really important as we start looking at the climate projections, in particular with regard to extremes. We want to make sure that the data can be accessible for practitioners, for researchers, and of course there is a number of different portals and applications that exist now where people can download the data in a format that's usable to them. But we also want to present that data in a way that's relevant and understandable, again, in a context of indices that could be relevant for warnings, for advisories, present that information for geographic areas that may be more appropriate for decision scale, for decision-making scale, and also think about some of the more interesting, innovative ways to visualize data. So somebody who is responsible, for example, for issuing warnings and advisories can start planning ahead and think about how some of those changing weather and climate patterns can affect preparedness and response capacities. So we talked a lot about exposure, but I also want to make sure that we talk about sensitivity and adaptive capacity. So here in the context of extreme heat, so here's another framework that we've developed where we unpack some of those complex concepts when we think about human capacity to deal with extreme events. And here we're looking at knowledge, attitude, practices, social capital, resources, community programs. And these are the types of data that we currently don't have. And so that information we need to collect through surveys or think about some other innovative ways to represent that information in spatial models and decision support systems. We also want to make sure that some of the adaptation and response strategies also get integrated into predictive models, and of course we're concerned about future climate, urbanization, and population. So probably the best way to look at the examples would be taking kind of a tale of one city. So this is Houston, Texas, where we've been working for a number of years. And so here we can start again integrating a lot of diverse data at the neighborhood scale, at the community scale, so we can look at all these different indicators of heat risk, ranging from urban heat island to prevalence of air conditioning, to income and other socioeconomic characteristics that might be relevant for this place. And we put this information in spatial models. Some of the new challenges that we started to address, and this is again something that we have to face when we think about data integration and solving some of those problems, is starting to look at integration between the Earth's data, social data, and also engineering and building information. People spend more than 90% of their time indoors, and so we need to figure out the ways where we can measure and model exposure indoors. And so we've been looking at that, again, through interdisciplinary approaches. There's a collaboration between building scientists, social scientists, atmospheric scientists, and public health practitioners. So we can, again, look at the household surveys, integrate some of that information about occupant behavior and indoor exposure into building models, and then inform epidemiological models that can tell us something about risk indoors. And also, as we're looking again at the nexus, this interface between climate, health, and energy becomes also very important. And so we need to start looking at what impact, for example, the blackouts or disruptions to energy grid can have on the population and on human health. Another challenge is that population is moving. Oftentimes we use census data as a snapshot, which is a snapshot in time, but people are moving, they go from place to place, they migrate from place to place, and some of the people have reduced mobility due to health conditions. And so this is one of the challenging questions for us, for our communities, how to incorporate some of the more dynamic socioeconomic data into the risk assessments, and what type of information can be used to really represent the socio-ecological systems in a more dynamic way. Here we're looking at the example in Chicago using transportation data, daily commute data, so we can better understand what would be exposure of the population in the city at different times of a day when people commute from work to home and vice versa. And another very important but highly uncertain area of research where there's a lot of scientific uncertainty is projecting the future risk into the future. And that's where I guess this is one of the research frontiers, using socioeconomic or socioclimatic scenarios through integrated assessments. So we can not only use climate projections, but also projections of the population, urbanization, and use that information to project future mortality rate. So we can understand what types of scenarios could be helping us to avoid future impacts, and what scenarios could lead to really significant impacts. So to summarize some of the concepts that I presented, so there is definitely a lot of data challenges. You know, I work in a GIS program, so we deal with spatial data. 15 years ago, there was a lot of discussion about data interoperability. How do we bring very diverse data together so the formats can talk to each other, so the system and platforms such as GIS can work with very diverse data. So first, you know, we're also expanding this conversation into data access and data usability. And all of those are very important because if the data are not relevant or usable, then the information that we're providing may not be answering the question that we're asking. And of course, data availability. I think, you know, we talked before that some of the data may be relatively available, but other data we don't currently have, and there is more effort need to be done to either collect or model or measure some of that information so we can start answering some of those complex questions. And in terms of some of the research challenges, even if we have all the great data in the world, there are still methods that we need to better develop to combine some of that observed and modeled data that exist at multiple spatial and temporal scales. It's a challenging question, and we don't have all the answers, but there's definitely some progress that's been happening in the last few years. Integrating some of the quantitative and qualitative social and behavioral data is extremely important, not only for developing some of the modeling work, but also to help us contextualize some of the models, but also look at the information at a very local scale so we can understand what's happening at the household level, at the community level, city level, and how we can scale it up to address some of the more global problems. I mentioned uncertainty, whether it's uncertainty with climate projections, with weather forecasting, or uncertainty with developing scenarios, or working with social data when we have limited information. So quantifying, visualizing, and communicating uncertainty is one of the big research areas and definitely a challenging task. I mentioned vulnerability, how we can expand a lot of work that's been done to incorporate some of the more dynamic vulnerability functions. And finally, again, asking some of the new questions that can lead to more actionable information. There's a lot of work that's been done on documenting different hazards, different risks, and vulnerabilities. And I would argue that we also need to make sure that the research that we do and the data that we bring together also helps us to address some of those complex problems. And that can only be achieved if we work across different disciplines, if we work with stakeholders, practitioners, and communities, and bring also different ideas to the table. So that's all I have. Thank you.
Thank you, Olga. That was very thought-provoking. Now, I would like to welcome Alex Desherbinen. He is the Associate Director for Science Applications at CITATION, which is located in the Earth Institute at Columbia University.
Well, thanks a lot, Michael, for inviting me to participate. I have no dynamic videos, so I apologize for that up front. If you need to get up and leave, that's fine. I also help to manage the NASA Socio-Economic Data and Application Center. So the function of this center is essentially to provide that bridge between the Earth and social sciences and to promote data integration between particularly NASA's remote sensing assets and the variety of data that come out of those, and the socioeconomic data across a range of areas, including primarily population. That's been one of our flagship areas and one that we've been working on for 25 years or more and increasingly perfecting, but also spatial data on infant mortality, poverty rates, economic indicators, and things of that sort. What are some of the data needs for integration? Obviously, different scientific disciplines use different data formats. Population data usually come in tabular formats. You can link them to boundaries. Physio-geographic variables such as climate, vegetation, et cetera, come in raster format typically. And then you get socioeconomic and biophysical data that are sometimes collected as points. And linking these data often requires conversion to common frameworks. That can be grids, polygons, and points. But this is a lot of what we do. We interpolate point data using Bayesian and other methods to create surfaces to Krieg. And in other cases, we take polygon data and we grid them so that they play nice with the remote sensing data. So I'm very obedient, and Michael posed some questions, and he said, please touch on these. So if nothing else, I should get points, right, Michael, for responding to your questions. So this was the first question he asked. Why is there need for data integration in human dimensions research, and what are the new possibilities that result from integration? So my approach to this was to give you a bit of a potpourri and kind of run through a number of areas and examples. Just to start out, this was a paper I wrote a few years ago, and basically I came up with a typology for the ways that population data are used with various types of biophysical data to understand the human dimensions of global change. So you can look at population data and time series data potentially as a driver of different types of changes in the environment. You could look at them, population data from the more vulnerability perspective or exposure to hazards and infectious disease and pollutants. We could look at population data as weighting exposure in different ways, and I'll give some examples of that if that doesn't make sense to you. You could look at vulnerability of populations exposed to natural hazards, and you can look at just masking places out on the planet that you don't really want to look at because they have population thresholds that are below or above the threshold that you really want to look at for a particular phenomena. So this was a study that some colleagues at CITATION were involved in where they looked at time series population data. They did a lot of work to basically get a good time series of a population because it's not, some people think population data just fall off a tree and you just kind of collect them and it's very easy, but actually it takes a lot of work to grid them and to make them all play nice with the biophysical data. But they did a very detailed study to look at what the drivers were of deforestation in Latin America using time series population data. This was a more recent study that looked at the different pressures and changes in pressures on protected areas. I don't have time to go into each of these individually, but suffice it to say that population was one of the variables they looked at to see whether in fact population had grown in a buffer zone around protected areas globally, and indeed it has in most cases. This was an index that we'll be actually disseminating soon through our NASA CDAC called the Development Potential Index, and it basically integrates population data from our gridded population of the world. So if you see GPW version 4, that's the acronym. And it looked at how assessing energy or hydropower and energy, wind energy potential, both in terms of the biophysical, like is there actually enough water there for hydropower or enough wind, but also where population's located, because it doesn't do you a lot of good to have wind power in an area where there's very few people. Urbanization potential has been measured by colleagues at Yale University, and they've done various interesting studies at looking at future urbanization and then looking at it in combination with flood zones or coastal areas, things of that sort. This was a malaria atlas project, kind of touching on John's area of work, and it looked at, they masked out certain areas that were underpopulated, because it turns out you need a certain population density for malaria to be transmitted. If there aren't enough hosts around, then malaria won't be transmitted as much between human beings. This was a meningitis study. John mentioned also dust from the Sahara, and meningitis is largely a dust-borne disease, and so again, population data were used to kind of map the spatial distribution of the likely areas to be influenced or affected by meningitis. This is some work that we did under NASA ROSAS funding, where we basically looked at and developed a pilot indicator, which is now a routine indicator that we developed, where we essentially weight the population exposure to air pollutants like PM 2.5, which is one of the most important. John can probably corroborate for the global burden of disease that it's one of the most important pollutants and health effects out there. And so if you weight the amount of people exposed to levels above the WHO standard of 10 micrograms per cubic meter, this is all those areas that meet that criteria, and then you add that all up by country, you get an index, essentially a population-weighted exposure to that pollutant. Other studies have used our data to look at exposure to air quality in the Indian subcontinent, which is an area where, frankly, they've essentially surpassed China during certain seasons and certain times of the year in terms of the acuity of the health pollutant threat. Wildfire vulnerability. This is a study that basically looked at areas that might be affected by wildfires, and then also the housing value or prices in those areas as an interesting study to kind of understand what kind of housing loss is very relevant for the Bay Area, I'm afraid. Flood risk and flood disasters. This was a study in Bangladesh, again, exposure related. The list, goes on, and I'm going through these quickly, but the point is that these kinds of data are integrated. This was a study that was really used for policy communication purposes a few years ago that I was involved in, where we were looking at the number of people affected by sea level rise in various megadeltas around the world. So the dark blue areas are 1 meter sea level rise for the Nile Delta, and the light blue is 2 meters sea level rise. And it's one of those particularly vulnerable regions that doesn't necessarily get a lot of attention. This was a study we were also involved in where we looked at, we actually modeled net migration on a decadal basis for this foresight report. And now we disseminate the data via the CDAC, but basically what you see is change in net migration for drylands globally. Guess what country in the world actually has positive net migration in drylands? You guessed it, US. It's one of the anomalies, but if you look at the bars, the US in blue, or North America, is consistently showing net migration into dryland areas, whereas the rest of the world sees it leaving those areas. This was a study that we did on vulnerability mapping. I think Olga very well framed kind of the issues around vulnerability mapping and the need for data. That prior slide was the various remote sensing inputs, and we published a paper which I don't have, well, there's a technical paper there you can look at, basically describing how we integrated these various data sources into a vulnerability map for Mali. We combine them into the kind of IPCC framing of exposure, sensitivity, and adaptive capacity and came up with an overall vulnerability map. CDAC disseminates literally dozens of integrated products. This is just a sort of a little bit of a sampler, but the one that I'll focus on is at the bottom, which was an interesting study where we looked at the nighttime temperatures within urban areas and outside of urban areas for the globe using satellite MODIS thermal LST land surface temperature data. And what we found was then used by a group that basically just took our data, analyzed it by climate zone, and published an article in Nature. So this is sort of the power of data integration. If you want more examples, please visit our citations database, where you can actually put in remote sensing and other terms and come up with a long list of application areas for different data. So this is the second question that Michael asked, which was, what are the major barriers to accessing and integrating data from a technical or interdisciplinarity problem? And again, examples are probably warranted. Some of the major issues that we face are mismatches in terms of spatial mismatches. I'll give an example of the coastlines. Scale mismatches are often an issue in the kind of vulnerability mapping that I do. Temporal mismatches, you have data from remote sensing that was just acquired yesterday, but your last census was a decade ago, and there are a lot of issues with kind of that static aspect of socioeconomic data. Inconsistent definitions or measurements across countries. And then you just have problems with non-existent or inappropriate data. Sometimes because you're working in an interdisciplinary context and you may not know another discipline well, you may use the wrong data or you may use it in an appropriate way. These are just examples for the Mali project I described earlier of the different units that we use. Communes, DHS clusters, which are these point data, and then we use data from very high resolution for climate data, but it was still only at 0.1 degree, or about 10 kilometers, that were based on FuseNet climate data, anthropogenic biome data that we disseminate, but each of these comes with a different resolution. Then you're starting to talk about spatial mismatches, scale mismatches, temporal mismatches, and all of those issues, which hopefully you document well in your final report. This is an example of coastal mismatches. So SRTM, which is not even right now considered maybe the most reliable or most accurate of the DEMs, but it certainly at the time we did this work was, has very different coastal boundaries than a lot of the census data that we work with. Sometimes the census boundaries go well out to sea, and we just have to lop them off at the coast. In other cases, the country boundaries vary. This was a research project I was involved with very recently where we worked with the World Bank to produce projections of climate migration globally. I won't go into the methodology. It used a population gravity model, and we produced these hotspot maps showing where various scenarios corresponded in terms of the red areas being largely in migration with 2030 on the left, 2050 on the right, and the blue areas being largely out migration based on these climate impacts. But when you look at the climate impacts data, we had to rely on colleagues, climate scientists at ICIMIP, which is based out of the Potsdam Institute for Climate Impact Research. And I trusted their judgment about the models we would choose and the inputs. Somehow this is advancing on its own, so I don't know what's going on. Maybe they're trying to speed me up. But the point is that later I talked to some other climate scientists and they said, oh, we don't believe that's going to happen there. So this is the kind of thing you get into when you come from another discipline and you have to work with the subject matter experts in other disciplines. And you begin to believe that, understand that you're wading into territory where there are very strong levels of disagreement. So how do we move the field forward in a way that will support and promote more efficient data access and effective integration? And this is my last slide, and we'll have extra time maybe for the other speaker. But basically, my answer is first, there's a lot of need for this data integration. A lot of the research we see gets very high profile attention, so it has to be done carefully and has to be done well and has to be well documented, and the uncertainties and things that Olga so carefully highlighted really need to be spelled out. But there's clearly a demand for this, and a lot of reports do state that this is an important area. I would say open data is critical. not just FAIR. I'm a big proponent of FAIR. I think FAIR is great, but it still only underscores accessibility. And so accessibility is basically about accessible to appropriate people at appropriate times in an appropriate manner. And that to me is not necessarily always sufficient. I would definitely be an advocate for open data over FAIR in most cases. Ontologies are important in understanding semantically how different data sets interact and what the meaning of the data sets are. Cloud processing is going to be increasingly important. We contribute our data to Google Earth Engine. We contribute our data to a NASA tool called Appears. In each of those cases, people can easily plug and play the data with other data sets and pull out important information from those. And then interdisciplinary and even transdisciplinary collaborations where serious effort goes into understanding each other's domains. We need to be able to talk to each other and really hash through what we mean when we're talking about various variables and come to some understanding about what data sets are appropriate to integrate with what other data sets. So with that, I will close, and thank you very much.
Thank you. That was a fabulous talk. Before we move on to our last speaker, let me just remind everyone that we are going to have time for questions and discussion after our next speaker, who is Erin Robinson. She is the Executive Director of Earth Science Information Partners.
Thank you so much. Thank you, Michael, for having me, and thank you all for coming to this panel presentation and for being part of Science Nexus Day as part of the Centennial event. So my name is Erin Robinson. I am the Executive Director of ESIP, the Earth Science Information Partners, and I think I'm honored to be summing up this panel this afternoon because I think what I have to say underpins what we've heard from each of the three speakers before me, and so I'm excited. I got into earth science data because I was really kind of obsessed with satellite imagery when I came to undergrad. And so yesterday afternoon, we heard from Barbara Ryan as part of the Leptic lecture, and she reminded us that countries have borders, Earth observations don't. And I think that being part of the Science Nexus Day also reminds us that even though we're all in our different sections, that our sections also, those borders are very permeable, and there's a lot of, I think, fluidity going back and forth across this panel and across the conversation that we can have today. So, without any planning, I was also in the air quality field, and so air quality and in long-range transport of smoke and dust needed lots of different kinds of data sets. We needed surface observations, we needed satellite observations and derived products, we needed models, we needed population data to show if people were being impacted, and all of that came with a variety of challenges. And so one of the things that it has a very Sisyphean feeling of needing to find each of those different kinds of data sets, needing to access them, needing to merge them. We've heard a lot about differences in spatial and temporal resolution, different formats, and all of that really has taken a lot of time. And so I think what we saw in the past three speakers is the results of that work, but really the results of that work takes a lot of time, many months, many years to bring all of those things together, and then there's just this sort of short window to do science. And so it's a lot of cleaning in order to get to the science part, which is often the exciting part, you know, when we're talking about understanding long-range transport. So there are these barriers to the user. The user has to find the data, access the data, understand how good they are, and then trying to merge them together. And it turns out, and these are science user barriers, and I think as Alex mentioned, you know, it's open science. We're really hoping to share these things. And as it turns out that all of us have come across those same challenges. So Alex also mentioned FAIR, and I will emphasize too that I think that it's also open, but that I think FAIR has given us, as from the informatics community, something to sort of rally around and a bridge between the work that we've been doing for the past many decades to the kind of challenges that we all encompass. And part of the FAIR paper said that there's an urgent need to improve the infrastructure supporting the reuse of scholarly data. And actually, I think that that infrastructure has many tensions on it. So as Olga mentioned, one of the exciting things in the Science Nexus is being able to answer new questions. But it's really comfortable to be in to have old science questions. There's I think the tension that I often feel between the technologist community and the science community. Some people think that from the science perspective that technology is just something that anybody can do. It's just a set of skills. But what I've seen in ESIP is actually that there's a craft and a practice, and there's a really talented pool of people who have spent their professional lives enabling the community. And so there is this tension, though, between the science and the technologist. There's a tension between the infrastructure budget to support science and the science budget. And as soon as we talk about supporting infrastructure, we talk about taking money potentially away from science questions. And I think that we need to know that we can answer more efficiently the questions that we're wanting to ask if we put money into the infrastructure budget. And then there's the tension between research and operations. And so what I mean here is that we are funded in the technology community often to push the edges of science data infrastructure. And what I think many scientists want is not for it to continue to change, but for it to be stable and operational. And so how do we balance those two things to continue to move the field forward and advance science, but in a way that's efficient, and we're not reinventing the wheel over and over as well? And so in that, I've modified this quote that it's not just there's a need to improve the global infrastructure, there's a need to improve the global collaborative infrastructure. And what we've all talked about today is really work that's done by a community. And by working together, we're able to use and reuse scholarly data more effectively. And that's where ESIP comes in. So ESIP, as I mentioned, is the Earth Science Information Partners, and it's a community of data professionals who have come together in around collecting, stewarding, and reusing data. And really what that means, I think, to AGU is that ESIP is a community of people who you can utilize and lean on to improve your science because they can help you with your data and technology. And CDAC is a member of ESIP, and I think is a really a great example of how that group has used data standards and best practices and has then also reached out to the community. So we see our members in this role of both looking inward across the community to agree on common conventions and standards, and then using that and efficiency that they gain in order to reach out to their user community, which they do so effectively. So ESIP brings people like CDAC and NCAR together across the data lifecycle, across the sectors, really to solve these common data challenges, and I'll cover a couple of those in my talk. This just gives you a sense of some of our members. So ESIP is funded by NASA, NOAA, and USGS because they understand the value of bringing together people across agencies and across institutions in order to solve these common data challenges. But what ESIP doesn't do is build science data infrastructure. So you might think it's a little bit odd that I just explained some of those challenges around science data infrastructure, but we feel that by connecting people across at the human level and at the organizational level and breaking down some of those barriers, that we're actually able to have a better, a more interoperable system and system of systems by agreeing on these lower layers. So ESIP does generate influential recommendations and work products, but what we don't do is we don't provide data. So that's one of the questions that I often get is, so what kind of data does ESIP have? Our members have data, and ESIP is really the community of bringing those people together. We don't sustain cyber infrastructure, and we don't develop standards, but our members use standards. So one of the, I think, original contributions that put ESIP on the map was something called the Data Citation Guidelines. And I have to say that as I sat and listened to our other speakers, I was really happy to see data citations in both Olga and Alex's talk in a couple of places. And so ESIP, the community came together, they created these guidelines, and then they were reused by NOAA and NSF and GEO as a backbone or a basis for more kind of restrictive is the wrong word, but more strict guidelines or directives that were coming up. And recently, those data citation guidelines were just revised and put out by the Data Stewardship Committee. So this work that I'm presenting is a community effort and is the work of many people, including Mark Parsons and others who are in the audience. So I think that I bring up citation because it's important, because we know that evidence suggests that citing data in publications increases the citation rate of those publications. And we know that it's a measurable way for giving credit to people who have done this work. So that's one example. Building on that citation work, ESIP, along with AGU, was part of a project called Enabling FAIR, which was around creating this common experience of submitting papers to leading Earth and space science journals. And it was a community-driven project with many, many partners. And it really had two kind of key objectives. One was that data repositories add value and have a consistent approach to supporting researchers with documentation on things like citation. And then the other was that as you're submitting a paper to a publisher, that the guidance to researchers was similar across all of the publications. So it wasn't that every time you tried to submit your paper to a different journal that you had a different expectation for how your data was documented, how it was managed, but that there was this consistency of what we're asking for across journals. So really this project was bringing together repositories and publishers. And there was a commitment statement, and many publishers and repositories have signed on. But what we're seeing is that this is changing the nature of collaboration and expanding opportunities to participate in science by having all of this additional data and by having technologies and tools that we can share data more effectively. Oops. So one of the things that I think we're struggling with now from the informatics community is how do we recognize and incentivize fair data practices, and I maybe augment this to open and fair data practices. And it feels a little bit like we're crossing the chasm. It feels like the informatics community has data citation guidelines, we have data management training, we have resources that are available, but often it feels like we're talking to ourselves and that there's a set of early adopters who are interested in potentially doing this, but that for the most part, the rest of the science community is still kind of in their, I would say, comfortable place of answering and asking old questions. So what I'm looking for, I guess, in Science Nexus is that we have new ways of asking questions and new ways of doing data management, and that you are partnering with data professionals, that you are willing to try new things and work in new ways, so that we make this leap into moving forward science in a new direction. So this leads to the researcher part of the enabling fair commitment, and really kind of the things that we're hoping to do with researchers. And this, I would say, is a culture shift that we are hoping to instill and inspire as we move into this next century with AGU. So it includes funder-required data management plans. So everybody has been probably required to create a data management plan, but often they then are put on the shelf and not really looked at again. It's working with your repository and having a relationship with your repository that happens long before you're thinking about publishing your data or publishing your paper, but that you have this ongoing care and feeding of your data. And then citing data and software and physical samples so that there's this connected web of research objects that are connected to you and that you're getting credit for the work that you're doing beyond the publication. And also all of the people that are supporting you are also getting credit for that work too. So one of the ways that we've tried to cross this chasm is through something called the Data Fair, which has been going on all week. It includes two parts. It includes a data help desk, which is in the exhibit hall 1329, if you want to stop by after this, which is a place where data professionals are coming together collectively to answer questions that people have as they think about using and managing their data. It also has included town halls, which are in an Ask Me Anything sort of style where, we really are hoping that we're getting useful information out to the scientists on how they can manage their data, talk about data management plans, talk about sort of anything that's affecting you and your workflow, and hoping to amplify and increase the productivity that you have with your data. So that's one way that we're trying to do this. I'm curious, and I would be curious, I think, in the conversation that we have on what are other ways that we think about changing culture so that we do affect change and have new and really interesting science. So I will end with one of my favorite quotes, that if you want to go quickly, go alone, but if you want to go far, go together. And I think that by working with data professionals and scientists across this nexus, we really have the opportunity to go much farther together. So thank you very much.
Thank you very much, Erin. That was a wonderful quote for us to end on. Now we're going to open it up to questions from the audience who I cannot see because of that light up there. But do we have a roving mic that can go out there? And I will.
Hello, my name is Patrick, and one question that came up for me as I've gone through the poster sessions and listened to the oral sessions is whether or not you guys on the panel could figure out a way to coordinate all of those posters and all of those sessions such that the information is integrated.
That would be, yeah, I mean, that would be quite challenging. I'm not sure that the five of us are going to do that. Maybe I would put that, maybe ask for a little more input there. I mean, they're organized in the sense of, in the sense that we have them organized topically. But and maybe to the panel, are there any other ideas for how we might integrate things differently?
You know, one of the things that makes me think about is what I think Alex raised, which was the question of ontology. What's the ontology? What's the framework by which you're going to take such an incredibly diverse set of issues like AGU? AGU has started that ontology. It has swirls. It has different ways of doing that. But it's really an AGU issue, right? It's not a five of us issue. I think there are ways it could be done as people are submitting abstracts. If there were an ontology that you could link yourself into, there's somebody's pointing and saying, anyway, that just some quick reactions.
Yeah, so one of the things that I'm aware of, I think that maybe is a start in this direction, is AGU has a preprint server called the Earth and Space Science Open Archive Repository, ESOR, is the acronym. And I think as we think about maybe smart posters, I could see having Jupyter Notebook style posters where things are clickable and runnable and the data would be accessible through the poster. I think this idea too of ontologies, of linking things together and helping people crawl in different ways would be really, maybe those two things together could be pretty interesting. Good question.
Hi, Aubrey Miller, NIH, and I wanted to applaud you for this great presentation today. And I'm thinking about the issue of bringing together the different data from the geo and earth sciences and the human health data, right? And one element is what is the efforts in human health information to create the same kind of ontology, the ability to bring information in the human health spectrum together, as well as the tension between human health and other data in terms of identifying people's personal information. And how do we handle that and think about the ethics across these boundaries with respect to these data information connections and sources?
Well, one way of doing that is aggregating, common way. Another way of protecting private information is to create enclaves where people can travel to the enclave and work with the data. So there are ways that certainly, in fact, colleagues of mine at Season were co-authors on a paper back in 2007 or 8 in, I think it was Proceedings of National Academy of Science, which looked at this issue of protecting privacy in an era of ever-increasing and higher resolution satellite imagery and all the other things that are exciting but also potentially troublesome in a world where you can now be tracked essentially continually using your smartphone, or others can track you, I should say, through the crumbs and digital things that you leave behind, as they call them, digital breadcrumbs now. So we have to be very concerned about that, and I think it's something that there's a very active public health community that is actively, ensuring or seeking to ensure that people's privacy is protected.
So from a health data standpoint, there's a lot of pieces to that. The first piece is just access and availability of data. And the issues that you have in a place like the United States are 100% different from the issues that you're going to have in a low-income country setting. And the approaches to this are very different. So in the United States, the vast majority of the data are private, held in private hands, and it's been very, very hard to access those. There are initiatives that have come about. The CDC now has some rapid, and the whole surveillance system in the United States is let's just say slow, and leave it at that. But there are some initiatives now to do some operational real-time reporting of, for example, some emergency room admissions that are coming in that are allowing more real-time operational things in a place like the United States. And in low-income settings, I think that there's, and I'm not an expert on this, but the DHS that was mentioned, there's a lot of efforts to standardize and digitize the collection of health data in low-income settings so that it's not on paper somewhere in a health department in a very remote place, but it becomes much more easily accessed. The issue of privacy, is a huge issue, especially when you're dealing with rare and more isolated diseases where people can be placed in space and time more easily. And one of the ways around that is increasing use of syndromic data. So the other substitute for actual outcome data is to use social media or internet-based data to look usually for not fatalities, but for less severe symptoms where the person with a problem is actually looking on the internet for answers to questions. And that's another way that you can get de-identified non-privacy. Well, we won't talk about how much privacy we give up when we do internet searches, another question, but another way to get at that avoids HIPAA, the legislation that protects privacy of health information.
I would add that it's an interesting question, and I think it needs to be, on a much broader scale, part of the ongoing discussion about data and privacy. I think that, as a scientific community and as a society, we've put an incredible value on, the privacy of medical records and public health data. But I also think that as individuals, it's very common that we'll give up privacy for something. We'll give up a lot of our data for a cool new app that we get for free and put on our phone. I think that, there's a very different set of standards in the scientific community than in the corporate world in terms of what's okay to do, in terms of scraping people's data and doing things with it. And I'm not saying that we need to lower our standards, but I think there should be a broader discussion that might help the public to understand, some of the benefits that they're going to gain from more, freer and more open data access that still has adequate protections.
Hi, Kai Chen from Yale School of Public Health. First of all, I would like to thank you all for this excellent session, especially John bringing the concept of precision public health. So regarding this concept, I want to ask John and other panelists, could you shed some light on the relationship between this precision public health and the other field on climate change and health, which we know for the climate change and health research is usually based on a large spatial and temporal scale compared to the precision public health. So what what's your perspective on the relationship?
Just a couple quick comments, and then we'll go down the line. So I introduced, first of all, the term because it's a controversial term and it means different things to different people. But I think that the idea of using, but I also introduced it very clearly to set a context of using Earth observations data, which are available in a very fine spatial and temporal scale, to be able to do the right intervention in the right place at the right time. I think that concept is perfectly applicable to climate change and health, because we know that climate change is a global phenomena that impacts in an incredibly micro scale, and that the interventions are primarily, the adaptive interventions need to be very local. The solution and interventions for mitigation need to be global, but the actual scale of the impacts and the interventions can be very, very fine. So I don't think there's any kind of discrepancy between the concept of precision public health and thinking about how do we apply it. The other thing I'll just say is that public health as a discipline thinks about the next second and maybe the last couple of days, and is not usually thinking decadally into the future. And so there is, it's very much the problem here now before me in a very resource-limited setting, and often a crisis at hand and people's lives at stake. So the mindset of the community is very different from the mindset of the climate community in many cases. And I think that there is a conversation that needs to be had to get the public health community to be thinking not just about the next minute, but also longer term in terms of planning and capabilities. And for the climate and earth science community to understand the preoccupation of public health people with the here and now.
So I just wanted to add a little bit more in the context of integrating health data, health information with also social and behavioral sciences, because a lot of times, even when we look at health data, we do have to look at the data in an aggregate form. And so, but when we, for example, do the household surveys and we try to understand some of the behaviors that may potentially lead to the health outcome, it also helps us to intervene at a very local scale. And so that's where I think there is a very interesting opportunity to integrate not only health and climate sciences, but also health, climate, and behavioral sciences. So kind of looking at the precision from a little bit different angle, looking at how do we understand what potentially have led to a health outcome and where can we intervene to avoid that in the future.
Hi, this is Amanda Quintana with the U.S. Global Change Research Program. I just wanted to know if the panelists could touch upon any platforms that exist right now that would be easily able to integrate existing data, and who takes the lead, and how can other platforms come together to bring it into one space that everyone can access?
Say a word. Good question. I mentioned too, basically Google Earth Engine obviously increasingly incorporates not just satellite remote sensing data, but data like the data that we produce on population. And they'll probably continue to expand, at least in a gridded format. They even support some vector operations. Appears, which is the tool I mentioned that NASA LPDAC, which is the Land Processes DAC, produces, basically allows you to extract data for time series at a pixel level or at an area level for a huge number of parameters. So if NDVI is one that constantly comes up, but you can look at land surface temperature or even aerosol optical depth, I think. There's also Giovanni, which is a tool that is supported by Goddard DAC, and that is more for atmospheric data. But these tools, actually, Giovanni's been around for about 15 years. It's amazingly not complicated. It's amazingly simple, but provides the ability to extract data for very complex operations simply. And this is where the Sisyphon kind of moving the, all the data prep and things that we used to sweat a lot about has been essentially, the barriers have been removed. I'm sure I'm missing other cloud platforms, so please, you have the climate inspector. And
Yeah, I might also mention the US Climate Resilience Toolkit. So that's a very nice collection of different tools and applications. But one comment I was going to mention is that there's a bit of a trade-off between having just one kind of one-stop shop type platform, which can become really crowded and really unusable, to having kind of more distributed tools that may address different questions and different problems in kind of a more kind of a targeted ways. So I don't know if there is like a kind of holy grail one platform that exists for every data that's out there, but there is definitely a lot of different data portals and tools and applications that help to make the data more usable for the, for the community.
Yeah, I think that that's actually a really important point, that there isn't one single one-stop shop, but that I think one of the things that we've seen across the community is that there's a convergence of using different data access standards and documentation standards. And when you do that, then you can curate, you can have a value added effect too by curating specific data sets that are useful for your community. So I think the Climate Resilience Toolkit is a nice example of that too.
Just two little things to add on in the health side. One major source of health data that is not necessarily integrated with the Earth observations data that is being used for a lot of these things is the Institute for Health Metrics and Evaluation, the GBD data. It is modeled data for the most part, and it's just from one source. But in terms of global reach for people looking at global questions, I think that's one place to look. And I just want to give a shout out to the CDC team that has created the Environmental Public Health Tracking data portal, which is one of the places where they're trying to grapple with the problems of different spatial jurisdictions of health data and environmental data. It's not a one-stop shop by any means, but it's just a place where that kind of integration work's going on.
Hi, Tom Carringham, economist at UC San Diego. I study the economic impacts of extreme events, and there's a bill that is making its way through Congress. It was passed by the House, H.R. 1984, which is the Disaster Act, or disclosing aid spent to ensure relief. And I'm wondering if any of you were consulted on this act. I think the idea is that it collects all of the data from all of the different federal agencies following disaster events and puts it all in one place where people can use it. And I think it's a great idea, but the devil is in the details. Do you have recommendations for how to implement something like that?
yeah, I think it's also, I agree, I think it's a great idea. I've never heard of it. So thank you for bringing it up. One thing I can think of is, well, from just selfish point of view, one of the things we're always looking for when we're doing vulnerability mapping, and Olga and I actually worked on a paper we published recently on the issue of vulnerability mapping, and is validation data. And very often, vulnerability maps are supposed to be predictive of where harm will occur in the future, but we often don't have any idea whether that actually borne out in reality. And so having a database that kind of collects damage information could be very useful. Did they stipulate where this data is going to be housed, or do you know?
Hang on, got a mic coming to you.
Thank you. It's to be collected by the OMB, and I think it's to be housed in a way that's accessible to everyone. My concern is that it will be an annual report of how much was spent by each agency rather than broken down into any kind of disaggregated form that would be actually useful.
Well, I think another question, and I don't want to dominate, but another question is, whether this can be useful in understanding whether we are repeatedly paying people to reconstruct houses or rebuild in areas that we can see. And this is one of the big issues in disaster, data and research, is often collecting those data from multiple agencies is almost impossible. But real questions are being raised now about whether we should be reconstructing year in, year out after every flood that occurs. And that's political waters, and I don't want to go too deep in that, but I just...
So we have a question from the AGU app. It's about metadata. Can you comment on the role that metadata has in data integration?
I'd love to kick this one off. I think that data documentation has a critical role in data integration, and I think that it's a really interesting thing. So the chart that I showed at the beginning of my talk, those 4 different data sets, they were not intended for my use, right? They all had different original scientific purposes, and I was pulling them together for understanding that long-range transport of smoke and dust. And without appropriate documentation, it's really difficult, if not impossible, to combine data sets together and to achieve understanding. So I think we talk about, documenting for discovery, but I think that what integration really needs is document for use. And the other thing that I'll say about this kind of documentation for use is that one of the terms that gets thrown around right now is analysis-ready data, and that is this meaning of, being able to easily integrate these things together because of their format. But I think it's that critical understanding that comes with the supplemental information that we need to be using. And so I would encourage everybody that's creating data that you don't skimp on the time that you're taking to document that data.
You're here. And just, you conflated a little bit metadata with documentation. I think structured metadata is great, but it won't, as I think we're trying to say basically, and I agree with you completely, is it's not sufficient. It's necessary, but not sufficient.
Super. Yep, I agree
So we've spent quite a bit of time at CDAC, basically, partly because we got feedback from this thing called the American Customer Satisfaction Index, ACSI, which basically said, look at your data, great, but I don't understand, how you constructed them, how you built them, blah, blah, blah. And so we said, okay, we get it. So we started actually creating mini journal articles for every data set. So you're welcome.
You have the consumers over there.
Right.
Within the Global Change Research Program and our interagency climate change and health group, one of the first things that we encountered when we were created in 2009 was this challenge of data integration, and we had a whole data integration work group. And the first project that we did was actually called the Metadata Access Tool for Climate and Health, because number one, we weren't smart enough to do data integration of the data itself, especially 10 years ago. But number two, this issue of just the central role of well thought out and actually filled in metadata fields as being integral to the usability of all these disparate kinds of data just became very, very central. And we pulled together, I think, 16,000 different data sets from across all of the federal agencies, and it actually drove us in the development of an ontology to be able to combine all of these different kinds of science and data and health data. Unfortunately, that project kind of withered on the vine when the Climate Data Initiative came through and the Climate Resilience Toolkit came through. But it's something that we probably need to, I think it is so central, and it's not just, it's number one, having a good ontology, two, having the metadata filled out, and then the other nuances of documentation, whether that is formally in notes in the metadata or about the limitations of the data set, all very central to the usability.
Yes, and we work a lot with spatial data, and especially when we try to integrate atmospheric data models with GIS data, that's where the metadata and how, spatial referencing, how that's included, that can make a really huge difference how interoperable different data are. So that's definitely a huge, huge part in bridging all these different disciplines together.
I would just quickly add that I think how you do metadata and documentation matters as well. I think CDAC is a good example where when people go there, the metadata and the documentation is fairly friendly to a broad range of users because it's designed that way. There are many remote sensing data sources, on the other hand, are much more narrowly focused to, to a community of experts. So I think that's something that, we as a community should be thinking about more as we do these things. And I would also add that, there are other things like vignettes or data recipes, other kind of value adds that you can put on top that can also help to grease the skids, if you will, for people to get in and start working with those data.
So we have another question from the AGU app. It states, many data sets do not contain information on accuracy, at best in metadata. Can we improve this to make it integral to the data?
Accuracy for what? I think there are, I'm being facetious, I think there are, like in remote sensing, there are clear accuracy metrics. On the other hand, in the area of like population data, we found that we're really struggling with how to validate population grids because, well, first people move around, and so it's validation for what time period, and we're working on it, and we want to get there. But there's also this concept of fitness for use, and that's maybe more than I want to unpack right here, but I think most people who work with data are kind of aware that you can use data for some purposes and not for others, and so that sometimes that may be a more useful concept than some objective benchmark or validation metric, which cannot always be achieved anyway. So I'll sort of leave things there because I'm sure other people have some thoughts on this.
Yeah, I would just add, that's an excellent question. It's an important question, but it's an extremely tricky question. Doing statistics and confidence intervals with geospatial data sets is not easy. I don't think anyone has figured out the right way to do it. And I think sometimes you hear people asking for, well, I'd like a confidence interval for each pixel. Even when we, like with non-spatial data, even when we have indicators of uncertainty, like confidence intervals and p-values, then we in our human nature tend to take those and horrendously abuse those to the point where people are now telling us, no, don't use this anymore. But I want to echo what Alex said. I think it comes down to utility. And I think we need to frame the questions about accuracy. Like one question we might often ask looking at a population map is, all right, are there places where we know the underlying data is pretty good? Are there some places where, for a variety of reasons, this is much sketchier? And I think we can deal with that in very practical ways. Maybe some levels of uncertainty classification. Hey, be careful if you're looking at this place in the map. But a good point thank you, app.
I mean, I think this is where you can't take humans out of the equation. I mean, I think that what we're saying is that just as there's no one platform that's going to fit every kind of data that we're going to ever use, there's no way to, I don't think that there is a way to build into the data the deep knowledge of the nature of those data, their limitations, all of the nuances that everybody in this conference has spent many years of their lives understanding. I think that's where we have to have multidisciplinarity. We have to have the humans involved in order to really be able to use data in a way that understands the accuracy. We can't, if we had 100% accurate data on everything, then we really wouldn't need experts. It would all just, we could just machine learn it all and it would all be done.
Yeah, so one example of that is some work that ESIP's Disaster Lifecycle Cluster has done. And so they've been working with data experts, and they've created something called the operational readiness levels, which is really this fitness for use. And they've been starting to apply those levels to some Earth observation data so that industry partners like utility companies could be ingesting those things and they would be knowing what they're getting. But I think one of the things that I'm adding to this as I've been listening to this little bit of the discussion is that I think it's really provided us a tool to have a conversation with the users about what they could expect from the data.
Hello. So my name is Laureline. I'm actually asked the last questions. So if I could just specify my question. I'm thinking of a very practical example. The water use numbers from USGS, for instance. They're notoriously inaccurate, but they're the only numbers that we have. I've been discouraged by USGS employees to use them, but that's the best thing I can get. What I know is that certain states do a tremendous job getting those estimates, whereas other states do not. So what I'm sort of asking and begging for, so that I can do proper integration of that data, is with each state or each county level measure, I could just have a rough estimate on how precise it is. And we're not talking down to each pixel at a very, I understand what you're talking about is very technical, but here we're talking about states where the errors are around 60% of errors and others are around 5%. So it'd be nice to be able, I understand the struggle in getting the information, but we need, from a metrology point of view, for each measure, you should have confidence intervals next to it.
Yeah, so you're, I guess, just to make sure we understand, with water, are you talking about agricultural water use or human?
It's a data set that comes out once every 5 years. It's broken down by water sectors, but even the aggregated numbers have that. So it's a volume per year that is used.
Yeah, I mean, I guess I can't speak to it directly. I'm not familiar with the data set, but, you know, there are other data sets like that too. For example, the USDA county level data on yield and areas planted, for example. There's some voodoo that goes on underneath there, and to really understand it, you have to like show up at the, you have to show up and find them and talk to them about it, and then you get to look into the sausage factory. But I mean, I guess I don't have a solution, but I would agree with you. You know, that is, I would think that something could be, something could be done there.
I think it could change the behavior of individuals, because sometimes it is voodoo and you have 200% of errors, and that's fair. Maybe that's the only thing people could do. I just want to know that.
You wonder if something like that could be opened up to a wiki, and crowdsource it. I've been out of academics for a while, and I know that the feelings of the collectors of the data about the data can sometimes be a little pointed. And so saying that some data are better than others or more accurate than others can be problematic. But for certainly government sources of data, I mean, it's true of, I think it's true of all the different sectors. It's true of health data. There's tremendous variability among states and counties. And if there were a way to, for a group like AGU or something to create some kind of wiki where there was at least a discussion, again, the accuracy of those data points are going to be also questionable, but that's why you do a wiki, to somehow refine it over time. Maybe that's an approach, to do it across sectors and not, not have it quite so specific.
So I guess what I wonder is it back to the metadata issue, that what you're looking for is another set of metadata that talks about quality. And so there are standards that are being developed and used to document data quality, and that could include those information, so that when you access the data, that you also access the metadata about the quality of the data. And then I think the idea of having a wiki is interesting. I think we get to the sort of population size here of how many people are providing feedback. But there are also, people are looking at having user feedback for data sets, and kind of this Amazon book page for a data set that you could understand, the kind of qualitative quality of it. But good question.
And I don't have an answer, but I just wanted to say thank you for this question, because I think you raise a very important aspect, that even in a data-rich environment, what often we deal with is inconsistent data, whether it's accuracy or what type of data being collected. And I think for us, I know it's a challenge, especially when we look at case studies or we work across different cities or states. It's very difficult to do this kind of intercomparison. For example, when we look at climate vulnerability, it becomes challenging to do proper intercomparison, so we're comparing apples to apples. So thank you for this question. I think you raise a very important point.
Do we have any more questions?
So we certainly are able to take more questions from the audience if you want to raise your hand. In the meantime, this is another question from the AGU site. Do you fear that gradually modeled data could be more prevalent than observation due to facility of access and appearances of completeness?
Could you repeat the first part of that question?
Certainly. Do you fear that gradually modeled data could be more prevalent than observation due to facility of access and appearances of completeness?
I think maybe it's gradually, comma.
Yeah.
Model data will become more common.
I think so. Got it. Okay. Not gradually modeled.
Yes. I mean, anyone who's used, climate reanalysis data, they, especially in Africa where I do a lot of my mapping work, knows that they're based on woefully incomplete observation networks, and they're interpolated over vast areas, and people accept them as valid because they're out there and they come from a reputable organization like the Hadley Center or wherever. I'm not blaming any of them for doing it. I think they're doing us all a great service. But I still think it's up to the user to some degree to educate. I mean, Michael talked about the shoe leather approach, which is you show up or you call or email the PI behind a data product and say, I want to use it for this purpose. And hopefully they'll answer you and say, that's completely inappropriate use, or yeah, go ahead. That's within the realms of what we consider appropriate for that data set.
Other questions or responses? If there aren't any right now, I guess I might put one to the panel. We've covered a lot of interesting topics, and just from a personal perspective, it's been a while now since I kind of crossed over from geography into the health environment interaction world. And when I was starting out, I really the kind of that gulf, the gap between the geosciences, earth science data, and for me specifically, infectious diseases, public health was apparent, and I kind of milked that in proposals and papers, and I feel like it's something that I've worked on, and a lot of many other people have worked on as well from a variety of different angles, but I feel like now looking back, you still feel like there's kind of that, maybe we've closed the gap a little bit or filled it in, but it's still there. So, in that realm, or thinking more broadly of bridging the gap between, earth sciences, climate, environmental data, and other types of data, I'd just like, in the few minutes we have left, maybe each of you could just say, give an example of what you've seen as one of the more exciting or important innovations, whether it is sensors, data processing, technical, something more on the human side.
We recently won an award from NSF on convergence research, which basically funded us in part to have these lengthy and very challenging discussions across disciplines. And that costs money. It doesn't just happen overnight. It requires multiple meetings. It requires very different, approaching each other's fields with humility. And so that's not really a technological response like bridging the gap, but I do think what I got, my last bullet on my last slide was basically that there's still a lot of discussion that needs to happen between people about the data that they work with and the kinds of questions and issues that they think are important to answer. Framing of questions, framing of research. So it doesn't quite get exactly to your question, but I do think that there is at least some recognition on the part of the funders that this needs to happen.
I mean, I would say I actually think it fits it perfectly. And I think if I were to answer that question, I might say something along the same lines. I mean, it's our human nature to cluster into, into groups, tribes, disciplines. And we get a lot of mileage out of that, because if you can huddle together with like-minded people and speak the same language, you can make a lot of, you can get a lot done within a certain area. But so we need to, the need to but break down some of those barriers and maybe recongeal, if you will, around what were previously the boundaries. Yeah.
I think maybe sort of going along that theme, one of the things that's been interesting to me to observe is the bringing together domain scientists with technologists and seeing how domain scientists are willing to adopt things like machine learning into their science and transforming science and having new understanding come out of using those new technologies. I think that's an exciting place to be.
I would also add that having a good collaborative team can lead to a lot of great innovation. Some of the more exciting work that we have done was the collaboration between atmospheric scientists, social scientists, spatial scientists, and I think that's where it takes time, for sure. It takes time to build common vocabulary, understand what everybody's talking about. So this kind of a sustained collaboration, interdisciplinary collaboration, is really important. And I think sustained, that's the key. And of course, I work with GIS, Geographic Information Systems, and I feel like some of the innovation in geospatial technologies are allowing us to bring all this diverse data and do some really interesting, innovative research and develop visualizations that can help us communicate the science. So I think we have a lot of promising work in the GIS field.
So as a health person, you were asking what have we seen over this time that seems striking. And here at AGU, I'm going to say that what has been really striking to me is how the earth science community has recognized the great importance of environmental exposures for health. To an extent that I will say that the biomedical research community has not yet. I mean, my institute, of course, is based on that, but in terms of the amount of attention and funding that goes to especially broader ecological impacts on health, it's relatively minimal. But from the earth science, we have, for example, the Group on Earth Observations has elevated health now to an initiative. We have the GeoHealth section, the first section in 15 years within the AGU, that has been exploding, now has 1,000 members. We have our GeoHealth Journal, which was not created from the health side, it was created from AGU side, which is award-winning and just ascending very rapidly. So I think that as a health person, I'm feeling the love and I'm feeling the pull. And I think that is the force, and of course we have programs like NASA and NOAA that are funding health researchers to use their data. I think that for the health and the Earth observations and the social data is the driving force of the last 10 years, and I think we're making good progress, and I think maybe we'll cross a threshold and everybody will get on board.
Thanks, John. And yeah, to wrap it up, and you've kind of led into this, I think AGU, embracing the Nexus, which includes GeoHealth, as well as a variety of other interdisciplinary sections, and giving us the Nexus Day, and creating the environment where we can have sessions like this, and where we can cross some of these boundaries within our professional space. So I guess let's finish with a thanks to AGU, happy 100th birthday, and thanks to all of our speakers for being here. Really appreciate it.
And thank you for organizing.